Okay, well, thank you very much, and I would like to start by thanking the organizers of this wonderful conference. Thank you, Ferenc, Karsi, Victor, Blodek. It's a great pleasure to be here as usual, as always in Budapest. It's a wonderful place. And we are getting here together to celebrate the birthday of these three wonderful men here, Gabor, Endre, and Ted Bistrisky. And these are nice people, and I have the fortune of know them, the three of them. Unfortunately, I haven't had the chance to work with neither Gabor nor Endre. However, I have not met them from a long time, and I'm very grateful for that one, for that part. And but I have had the fortune of meeting Ted. This is a photograph of my first conference ever outside of Mexico, and the first time I speak in English at all. And it was a wonderful conference. You can see Wendy is there, Robert Dawson as well. This picture is around, Asia is there too, right in the middle. This picture has to be around 20 years old, if I'm not mistaken. So this is
1997, I think, in Dalhousie.
Yes, in Halifax. So here is Dancer, Ludwig Dancer, and Grunbaum are there in this picture. So some of us have changed a little bit, but not much, I would say. And some years after this picture, at this moment I was a grad student, and then some years after this picture was taken, I had the fortune to go and do my postdoc with Ted. At the beginning, I was going to be there for only 10 months, and I ended up being there 7 years or more. So that means that it wasn't that difficult. It wasn't that bad to be there. Sometimes in life, you have to be grateful of what you encounter, and I must say that meeting Ted was one of the wonderful things that had happened to me in life. It was not always easy, I should say that, but it was a great thing in my life. It has opened me a lot of windows, and being here is one of those. Meeting wonderful people and having good friends like Ferenc is one of those things. So thank you, Ted. This picture was taken right when I arrived to Calgary. With some friends made a party to welcome me, and this is a picture taken over there. So this is pretty much a very good picture of things, how things develop. Anyway, so thank you and congratulations. So I will talk about HELLY'S theorem, as I said in my title. And HELLY'S theorem is by now a very classical theorem that perhaps all of you have heard. So this is a theorem about finite families of convex sets. Of course, you can think as there are possibilities of extended to infinity families if you wish, but for the sake of this talk, I will stick with finite families. And there are some generalizations of this theorem in topological senses where they extend convex sets into more wide possibilities. But I will stick with this format in this theorem. So this theorem is the best possible in every possible sense. D plus 1 is that number that you have to have. So if every d plus 1 element of my family has a point in common, then the whole family have a point in common. That's a classical theorem I'm going to use. So HELLY'S theorem has a lot of generalizations and have fit many mathematicians over the time. And these are just some possibilities of extensions of this theorem. Fractional, Helly, PQ problems that maybe Andres will talk about. Helly over subsets in RD that I will talk a little bit about. Colorful Helly theorem that it has been widely studied too, but I will not touch it. Helly-Galai type theorems, which I will touch a little bit. Transversal problems, which are one of the topics that Ted Ferenc and I have worked a little bit, but I will not touch it today. So I have chosen one of my favorite families of convex sets just because they are quite simple to understand, and sometimes it simplifies things. So if you're stuck and you cannot do anything without, you're stuck, then this is a good family to work on. So boxes are precisely what you are imagining, but not exactly in any position. So what I want for boxes are parallelograms, but all the sides of my parallelograms must be parallel to the x's, okay? So not located in any way, but for example, in dimension 2, this is my family of animals that I will work with today, or mostly today. So this family has very nice properties, and I hope I can at least convince you a little bit that this is a nice family to work on. Sometimes it gets more difficult, but the first fact is that this number, d plus 1 over there, could be simplified in general. So asking for every 2 plus 1 having a common intersection is asking too much. So if you ask that every 2 of them have a point in common, then you can guarantee that the whole family has 1 point in common. And this is pretty easy to see. If you say you are in dimension 2 and you project over one side, so once you project in dimension 1, this says that every 2 elements must have a point in common. So if you project and every 2 of them have a point in common, then you will find a point that is in common to the family. Same on the other direction, and then you continue and you find a point that is common to the whole family. And you can do a proof of that in every dimension, of course. So in this case, 2 is enough. I don't need d plus 1. So this is the first fact, easy to see. Before I continue, let me define what a piercing is. So piercing for this talk will be a set of points such that every element of my family contains at least one of these points. So for example, if I have these convex sets, these 3 black points in here are piercing the family because every single element of my family contains one of these points. So if we want to go a bit further and we want to find the minimum number of points, that's what we're going to call the piercing number of my family. And it's usually denoted by tau of f. Okay, so in this particular case, the piercing number is 2, for example. Okay, so one very nice, simple exercise, but still very beautiful, is this nice proposition. If you want to find out the piercing number of a family of boxes, then this is going to be equivalent of finding the chromatic number of the intersection graph of the family. So take a point for every element for every box, and put an edge between 2 boxes if these 2 boxes intersect. If they do not, then you don't put any edge. So if you look at this graph and you look the complement of this graph and you find that the chromatic number, then that's going to be exactly the same as finding the piercing number of the family, which is a very nice, simple result. Another fact is is that this graph, so suppose that in your graph of intersection, you find a square or bipartite piece of K22 graph, complete K22 graph. Then observe the following. Since these two do not have an edge in common, then it means that you have one interval on one side and another one on this side. So A and B must be disjoint. On the other hand, C and D must be disjoint too, but C intersects A and B and D as well. So if you are in dimension 1, this is impossible. So in the case of dimension 1, this means that you must have an edge between C and D. So in other words, if you have a K22 graph, then that's a forbidden graph on my set. Similarly, if you have a K222 as a graph, then, for example, in dimension 2, you can pretty easily see that that's also forbidden, right? Because these two gray boxes, in order to be, they must intersect. So that means that you must have an edge on one of these sides. So in other words, my graph, this intersection graph, is a K2223 as an induced tube graph. Okay, that's also a nice fact, but easy to see as well. Okay, so pretty much Helly theorem and all these things, we can talk about piercing problems. Of course, you can do it some other properties. For example, transversal theorems, I shouldn't put it here because it's not about piercing, but transversal lines intersecting, but same philosophy. So the first theorem, the first version I would like to talk about is what is known as fractional Helly theorem. So the idea is the following. I want to weaken it, the version of Helly theorem in the following sense. Instead of asking that every D plus 1 tuplet have a point in common, then I'm going to be a bit flexible, and I will say not all of them, but a fraction of them. So alpha of these D plus 1 tuple have a point in common. So the main point is, what can we hope for this fractional condition, right? And the idea is that, well, if F contains a subfamily G of size gamma of F, and this gamma depends only on alpha and D, then such the, what is it? Anyway, well, the family, it's the, okay, there is a such part of the family that have the intersection is bounded. Let me say it in other words. This theorem, which is known as fractional Helly theorem, is due to Kashasky and Liu in 1979. And it says precisely what I was trying to say. Okay, so you assume you have an alpha between 0 and 1, and this real number, and assume that your family of convex sets have alpha of these tuplets have a point in common. Then the family contains a subfamily of that cardinality, alpha over D plus alpha of D plus 1, sorry, of these elements that have a point in common. This theorem was improved by Kalai from this size into this one, and this bound is best possible. Okay, so let me tell you what to do next. So we want to find out if you have D plus 1 tuplets intersect, some of them, a fraction of those tuplets intersect, then there is a fraction of the whole family that has a point in common. So what we want is something similar, but instead of having D plus 1 tuplets, just the tuplets, because boxes, every two of them intersect, then the whole family intersects. Well, it turns out that this is not the case. So for example, if your family has size n, take n boxes parallel in this way, and n boxes parallel on that way. So half of them, half of the tuplets intersect, but there is no three of them having a point in common. Okay, so then say, well, we should then try to to see if we can find a fractional version of this or what's going on. So we start playing around and we come up with this nice theorem. So instead of alpha between 0 and 1, we get alpha between 1 minus 1 over t times 1, and then finding that there is such a fractional version. So as you can see here, I have some mixed feelings of this theorem. I'll tell you why. But first, let me tell you what was the fun part. So the fun part was based on two-rank graphs. So let me just tell you a little bit about it. So in 1941, Turan asked the following. So suppose I give you two numbers, n and r. So this positive number t and r is a number that guarantees that if you have a graph with n vertices and that number of edges, then you are going to be guaranteed to have a complete graph of size r. So the two-rank graph is, it turns out to be a complete R-partite graph on n vertices, whose cardinalities of these partitions are as equal as possible. And the number of edges of the two-rank graph is precisely that number over there. And there are some bounds known. I'm not going to go into the details. But let me give you an example. So suppose you want to find t and 3. So it means I want to find a number such that every time you give me a graph with n vertices, if my graph has that number of edges, then I can guarantee you that at least there is a triangle on my graph. That's the main idea of this thing. So for example, if you give me, 12 vertices, then 12 vertices, if you plug 12 over there, that will give you 36. So not all graphs with less than 36 edges have a triangle. But if you have more than 37, you are guaranteed to have a triangle, no matter what you do. So if I give you 36, a graph with 36 edges and 12 vertices, you may be clever enough to find a graph with no triangles. But if you have 37, no matter how hard you try, I will guarantee you that there is a triangle there. And the two-rank graph is a bipartite graph in this case. So for the particular family of boxes, and again, you look at the intersection graph of these boxes, then we were looking for T N K D over there, which is the maximum number of edges of this graph with the same philosophy, with the property that is that there is a complete graph. Well, I wrote that is not a complete graph, but you can also think in it that way. That guarantees that having a complete graph of size k plus 1. So with that in mind, we proved that this, the maximum number of edges is bounded by that number over there. So that was fun. And the idea was using precisely those properties I told you about boxes. So in the case of having a bipartite graph, I already convinced you that we cannot have a square as an induced subgraph. So that was forbidden. And same thing in general. If the two-rank graph is a complete bipartite like that, and we are talking about, in the case of boxes, then you know that at least in one of the partitions must have a complete graph over there. So using those facts, we come up with the proof that this limit exists, and therefore the theorem I showed you before was true. So once we were about to submit the paper, Janos pointed out to us that theorem we were trying to show come up directly from a theorem of them as a corollary. So I say, well, okay, it's not nothing new, but anyway, it comes from a corollary of them, but the methods we used were completely different, and we have our hands dirty, and it's worth mentioning. So we publish it anyway, and some of us were very innocent, and then we find out that there were some bad news. In 1980, Kachowski proved exactly the same result, and in 1988, Eckhoff already have extended that same result. In 2007, Eckhoff as well to generalize that theorem. So, so we were sad afterwards. But anyway, sometimes when you're ignorant and innocent, then you have the chance to continue working. So with the same ideas, some part of the team continue working, and we already knew that in the case of dimension 1, we know precisely what the bound is. So we went a little further and tried to find out what exactly the graph, the intersection graph, looked like. And we find out that if you can see over there, that's the edges of the complete graph, and then minus something. So we decided that in the case, the graph must be something like that in the case of dimension 1. So these are n minus k plus 1 isolated points, and then a complete graph with k minus 1 over there. So if you realize that as intervals, then you have k minus 1 intervals that intersect each other as in a complete graph, and then n minus k plus 1 disjoint intervals that each one of them is intersecting each one of these edges. So then we look a bit further, and then we prove this sharp bound, which is not, it's sharper than the bounds that Eckhoff found that. So anyway, being innocent sometimes is good. So let me give you an example how this works. So suppose you have 20 vertices, and your k is equal 4, so, and your dimension is 2. Let's just make, so we have boxes in dimension 2, and so according to that formula, that's what we should get. So the THEOREM graph is going to be as follows. So this is going to be the classical THEOREM number, which, as I already convinced you, is a bipartite. The green part is a bipartite graph. And then this part over here is the one I showed you before, the blue part. So that is going to be a complete graph that is joined by a set of disjoint vertices over here. And the representation of the realization of the graph is the one that you have at the right, precisely. Okay, so that was good. So let me go a bit further to some other definitions. So Helly over subsets in RD. So the idea of here is, instead of having points anywhere in the Euclidean space, I'm going to narrow down my allowed points. So I cannot place my points anywhere I like. I have to say it before which ones are my allowed points. So one of the first theorem on this direction is due to Dognon in 1973. And this theorem was rediscovered by Bell and Scarf in 1977. And it says the same philosophy. So you have a family of convex sets in the Euclidean space, and suppose that every 2D of these elements of the family have a lattice point. Then there is a lattice point in the whole family. So here you can see that this 2 to the D is best possible. So if you have this half space, this one, and that one, every 2 or 3 of them have a point in the lattice, but the 4 of them, the intersection of the 4 of them, do not have a lattice point. So then 2 to the D has to be the best number possible. Then we say, okay, what can we say about more general sets? So the first step was to work on dense sets. Okay, so let's say now instead of having all real numbers or all integer numbers, I'm going to assume that my set of points is a dense set. For example, everything, all the whole plane except the point at the origin, which is pretty dense. So in this particular, say, every 4 of them have a point in common, but then there is a point in common in the dense set. The theorem, the proof of that is not too hard, but unfortunately, it's not true the way it is in dimension 3 or higher. And this is just an example of that 4 is best possible. And unfortunately, this theorem is also not true in a discrete set. So if you gave me an arbitrary discrete set, so for example, my allowed points are these points over here, and my convex sets are these n-gons, okay? So you can see here if I take the intersection of every n minus 1 of these gons, they have a point in common on my allowed region, which is this one over here. But they do not intersect on an allowed region, okay? We also play around with differences of lattices. And in dimension 2, we show that if every 6 convex sets intersect on a difference of lattices, so if they intersect, say, for example, in one of these points, then there is a point in common on the whole family. And this is just notation. So S is going to be my set of allowed points, and H of S is my Helly number, or my magical number. So again, we play around with some other more general differences of lattices, and this is in dimension D, and we found this bound over here. And okay, also play around with dense subgroup on R, and then if we get a subset of RD, which is a G module, then we also find some Helly numbers. Okay, I'm going a bit slow, so I'm just want to continue on. So let me just very quickly tell you what a Helly-Galite type problem is. The philosophy is the following. Suppose you have your favorite family. Okay? And then you have your favorite property, whichever that may be. And then you say, okay, I want to see if every subfamily of my family have that property for a certain amount of numbers. What can I say about the whole family? Does the whole family has that certain property? That's the main philosophy of a Helly-Galite type problem. So suppose that every subset of cardinality M, in this case, I'm going to ask to be n-pierceable. Is it true that then my entire family is n-pierceable? Well, Dancer and Grunbaum showed that this is not always true, not even for the case of boxes. As you can see here, if I'm in dimension D equal 3 or larger, and my piercing number is 3 or larger, then I do not have a Helly theorem for this case. So how about looking to see if there is a Helly-Galite theorem of this type of piercing number, but using the same philosophy of forbidden places. So for example, take your plane, and suppose I'm going to forbid you precisely this box over here, okay? So I already convinced you that if every 2 boxes have a point in common, then the whole family will have a point in common, but I have blocked precisely the point of intersection. So if I forbid regions, then I'm not necessarily going to get 2, of course. So, but I need to have 2 to the D in this case. So if every 4 in the case of the plane, if every 4 boxes intersect in an allowed region, no matter how my region looks like, then I can guarantee you that there exists a point in common of the whole family, no matter how crazy your region looks like. So I made a mistake here in this D1. I want to find out what happens with piercing 2. So with piercing 2, it turns out that, as in the case of Dancer and Grunbaum case, that there is no Helly theorem in that case. So what I want to tell you is I want to convince you that if you give me a number, I can come up with a set of points, and I can come up with a family of boxes such that every n minus 1 have piercing 2, but the whole family does not have piercing 2. So say you give me 20 as a number, then I can come up with this discrete set, which is weird. You will see why it's not that weird. But let's say I give you these points, and then I'm going to give you these 4 boxes. Why not? They are pushing things to the limit. And then I'm going to give you this other box, and then this other box, and then this other box, this one, and this one. And then I will put 2 vertical ones in this way. Of course, if you give me a larger n, then I will put more reds in this direction or more yellow in this direction. So I want you to observe the following. If I remove one of them, so say this gray, then the piercing of my family is 2. With these 2 black dots and my allowed region, you can pierce the whole family with these 2 points. Okay, so if I remove this red one, then again, this black point over here and that black point over there pierce my family. If I remove this one, then these 2 black ones, the one over there, this is not working, but anyway, the one and the one at the bottom and on the bottom pierce my whole family. Similarly, if I remove this one, I have 2 points that pierce my whole family, but there is not 2 points that intersect the whole family. And I can do that in general for every n. So unfortunately, even this theorem of Dancer and Grunbaum could not be extended for general sets for any general set in RD. Now this is a bigger family, same idea. So how much time do I have? 7 minutes. Okay, so just really quickly, I want to say a bit more about boxes. So first, in 1969, Robert tried to extend. By that time, the characterization of interval graphs was completely done. And all graphs that have are interval graphs were completely classified. And Roberts wanted to extend this classification into boxes. So he defined what the boxicity of a graph is. So the boxicity is a minimum dimension on RD such that your graph is realizable as boxes. So for example, if I have a cycle of length 4, then the boxicity of this graph is 4 because that's the minimum realization I have in dimension 2. So at that time, he proved that the boxicity of a non-complete graph could be defined as the intersection of, if you can draw your graph as an intersection of interval graphs, then the minimum k that you could do that's going to be the boxicity of your graph. So we try to extend that as a p-boxicity, which is, instead of having full dimensional boxes, I'm going to allow to have flat boxes, like pieces of boxes or intervals, or depends in which dimension. So we define what the p-boxicity of a graph is. So let me just give you this example really quick. So imagine you have this graph over here. The boxicity of this graph is 2, because that's the minimum dimension that you could define it as a boxes. But if you insist on having things not fully dimensional, then the boxicity, the one boxicity of this graph is this one. So it goes one higher. So this is a more, I don't want to go very much into the details. I have not much time. But basically, we extended Robert's theorem to see what are the properties that a graph must satisfy to be realizable as P boxes in RD. And with this definition, we find out some nice results in terms of the complement of the cycles. So for example, the complement of the cycle of length 5 is realizable in dimension 2 as 1 boxes, but any other cycle bigger than that is not realizable as 1 boxes. If you have the complement of the cycle of length 7, we can realize it in dimension 3, but it's not but no further cycles of higher length are realizable as lamins on any dimension, and so on and so forth. And this is useful because I already mentioned that the chromatic numbers gives you the piercing number of a family of boxes. Then if some cycles odd cycles are allowed, which means are realizable, then that gives you the chromatic number is 2, because odd cycles are forbidden. So using this fact, we were able to extend Dancer and Grunbaum theorem for a more general family of boxes, not fully dimensional. And that's all I want to say. Thank you.